Welcome to the second lecture of the Electric Spacetime Relativity video series, The Third Cloud Deep Within Physics, the Infinite Energy of a Point Charge. Lord Kelvin once pointed out that two clouds hovered over classical physics. The first cloud was the Michelson-Morley experiment's failure to detect the ether wind, which shook the space-time perspective of classical physics and ultimately gave birth to special relativity. The second cloud was the radiant energy divergence predicted by classical physics, known as the ultraviolet catastrophe, which ultimately led to the birth of quantum mechanics. Today, we are going to discuss a century-old problem hidden in the deepest depths of physics, the energy divergence of point charges. I call it the third cloud of classical physics. To dispel this cloud, electric spacetime relativity was born. It not only attempts to cure this century-old headache, but it might also evolve into a new space-time architecture that unifies relativity and quantum mechanics. Since the third cloud is the starting point for this entire new theory, today we are going to dig right into its roots. First, I'll sort out the fundamental contradictions of this problem for you. Then the AI will step in for a more in-depth explanation. Finally, we will uncover the ultimate key to solving this dilemma together. And a heads up, Episode 3 will be dedicated entirely to discussing this key. You might be thinking, since the trouble is caused by this volumeless point, why not just enlarge it a bit and turn it into a tiny sphere? The answer is absolutely not. If the charge had volume, the immense like charges repel force inside it would instantly blow it apart, making it impossible to exist stably. Furthermore, this would destroy the quantized nature of elementary charges. Because of this, even the most advanced modern quantum field theories have been forced to continue using the point charge model to this day. I need to remind everyone here, real electrons and other charged elementary particles do possess mass and spin, but looking solely at their elementary charge properties, their charges are indeed volumeless point charges. Today we are tackling the divergence problem of the ideal point charge, specifically to lay the groundwork for solving the energy difficulties of elementary particles down the line. This is an incredibly crucial step. But since the elementary charge can only be a point, a physics disaster strikes. According to classical theory, the electric field and electric potential at the center of a point charge are both infinite, meaning the total energy it contains is also positive infinity. Faced with this massive bug in the system, what has modern physics done? Quantum electrodynamics, QED, deployed a brilliant mathematical trick called renormalization to forcefully subtract this infinity. However, the heavyweights of the physics world weren't buying it. Dirac once sharply criticized it, essentially saying, "This is just a mathematical patch, not a physical solution at all. Are we really doomed to just keep slapping a band-aid on this wound forever?" The true answer has to come from a deeper reconstruction of our space-time architecture. Can we completely terminate this infinity from a pure physics mechanism while still keeping the point charge? Next up, I'm handing the floor over to the AI for a deep dive into this cloud.
I want you to imagine, just for a second, holding a single electron right in the palm of your hand.
Which is, quite a mental exercise.
Right, it really is.
Yeah.
But it's the absolute foundation of our modern technological world. Like the device you're listening to this very deep dive on, the servers routing the data, the whole electrical grid.
All of it.
It all fundamentally relies on the properties of that tiny invisible speck resting in your palm. Yet, according to the classical foundational rules of physics, that single electron contains an infinite amount of energy.
And we are not talking about like a galaxy's worth of energy here,
Ah,
or even a universe's worth of energy.
right.
The mathematical equations that govern electrodynamics dictate a literal, boundless, positive infinity residing inside every single fundamental charge in existence.
It's just wild to even conceptualize. So, welcome to the deep dive. Today, our mission is to explore one of the most fascinating, mind-bending flaws sitting at the very bedrock of modern physics.
A bug in the system, basically.
Exactly. We are looking into the infinite energy bug of the point charge. This is a mystery that has baffled theoretical physicists for well over a century now.
Oh, absolutely. It's notoriously stubborn.
And to guide our exploration today, we are drawing from a really fantastic source. It's the YouTube channel called Electrodynamic Spacetime Relativity, run by an independent theoretical physics researcher named Yingtao Yang.
Yeah, his work is incredibly detailed.
It really is. Specifically, we are unpacking the second lecture of his series, which focuses entirely on this exact problem, this infinite energy divergence.
And it is such a critical topic, too, because, I mean, this is not just some obscure edge case in a forgotten, dusty theory. The bug exists inside the idealized point charge model itself.
Which is pretty much the core of everything.
Right. It's an indispensable pillar of classical electrodynamics, and it's heavily used in modern quantum field theory. We literally build our understanding of the universe on the assumption that charged particles, like our electron, are perfect geometric dots.
Geometric dots. So, meaning they possess a definite, measurable electric charge, but they occupy absolutely zero spatial volume.
Zero. They are entirely zero-dimensional entities.
Which, immediately sets up a massive physical paradox for anyone listening. We are talking about packing a finite amount of electrical charge into a spatial volume that just physically does not exist.
There's no length, no width, no depth.
Right. So, playing devil's advocate here for a second, if packing charge into a zero-dimensional singularity causes this massive infinite energy glitch, the intuitive leap is to just give the electron some volume, right?
Seems like the obvious fix.
Like, why not just assume the electron is a tiny three-dimensional sphere, just a highly localized distribution of charge? Wouldn't that solve it?
You'd think so. Giving the fundamental charge a spatial distribution seems like a neat way to avoid the singularity. But abandoning the point charge model and spreading that charge over a localized space, like a tiny spherical marble, it actually triggers a cascade of new theoretical disasters.
Wait, really? Worse than infinite energy?
Arguably much worse, yeah. First off, doing that completely destroys the quantum nature of fundamental charges.
Oh, because the mathematics of quantum mechanics relies on fundamental particles being truly indivisible.
Exactly. If you give an electron a physical radius and a volume, you are implying it has a geographic structure.
Right, like a left side and a right side.
Yeah, and anything with a physical structure could, theoretically anyway, be sliced in half, which completely violates the very definition of a fundamental, indivisible quantum particle.
Okay, I see. So the whole quantization aspect just falls apart.
It does, and that structural implication leads directly to a second, even more catastrophic mechanical problem. I mean, we all know from basic science class that, charges repel each other, right?
Sure, two negative charges push away from one another.
Right. So if you take a single fundamental negative charge and distribute it over the physical volume of a tiny sphere, the different spatial regions of that exact same charge will start exerting a repulsive force on each other.
Wait, so the left hemisphere of the electron would violently repel its own right hemisphere?
Yes. The internal electrostatic repulsion would just instantly rip the particle apart.
Wow. So it would essentially destroy its own stability.
Exactly. You would need to invent some sort of mysterious internal binding force, something much stronger than the electromagnetic force itself, just to hold the single electron together against its own self-repulsion.
And I'm guessing classical physics provides absolutely no mechanism for what that binding force could possibly be.
None whatsoever. It's a complete dead end, which leaves theoretical physics totally trapped. The theoretical model destroys the stability of fundamental matter and breaks quantum indivisibility.
So because the alternative is just completely unworkable, modern physics is basically forced to retain the idealized point charge model.
Warts and all, yeah. Even our most highly advanced frameworks like quantum electrodynamics, they're all built on top of this zero-dimensional abstraction. We just have to carry the bug forward and deal with the mathematical fallout.
Okay, let's actually look at that fallout then, because the lecture notes provide a really clear breakdown of the mathematical disaster this causes using the most basic equations of classical electrodynamics.
Yeah, it's fascinating to see the math just crumble.
We can basically trace the logic step by step to see exactly where the universe mathematically breaks down. Where do we start?
So we start with the electric potential, which is often denoted as phi in the equations.
Right.
Around a point charge, the potential increases as you move closer to the source. The actual formula is phi equals 1 over 4 pi epsilon naught times the charge q divided by the radius r.
Okay, so the key takeaway for us there is that the potential is inversely proportional to the radius. As the distance gets smaller, the potential gets bigger.
Spot on. Then we look at the electric field strength, usually written as E. The electric field is the negative gradient of that potential, meaning it climbs even more aggressively.
How aggressively?
Well, the equation is E equals Q over 4 pi epsilon r squared, so it is inversely proportional to the square of the radius.
Oh, wow. So E is proportional to 1 over r squared. That's a huge jump.
It is. And then we arrive at the energy density of that electric field. According to the foundational equations, energy density, let's call it WE sub E, is equal to 1/2 epsilon times E squared.
Wait, E squared? So you are taking a value that is already governed by an inverse square law, and you are squaring it again,
Exactly.
giving us a field energy density that scales with 1 over r to the 4th power.
Yes. And this is exactly where the integration completely blows up in our faces.
Right, because to find the total self-energy of the electron's field, you have to integrate that energy density across all of three-dimensional space.
Right, you're calculating a volume integral to find the total energy E sub Q. And when you do a volume integral in spherical coordinates, it adds an r squared term back into the numerator.
Okay, so you are integrating r squared over r to the 4th, which basically leaves you integrating 1 over r squared.
Exactly. And the integral of 1 over r squared is negative 1 over r. The critical moment, the real disaster, comes when you evaluate that at the boundaries.
Because you have to integrate all the way inward to the exact dead center of the electron, right? Where the radius r shrinks to 0.
Right. You are taking the limit as r approaches 0 for the equation q squared over 8 pi epsilon naught r. And any fraction where the denominator goes to 0?
It shoots off to infinity.
Positive infinity, exactly. The math strictly and unavoidably dictates that the total electric field energy contained within the point charge is infinite. The potential diverges, the magnetic field diverges, and the self-energy of the electromagnetic field completely diverges.
But observationally, the universe is perfectly stable. I mean, the electrons in the device playing this audio right now are behaving normally. They aren't radiating infinite energy and consuming the solar system.
Thankfully, no.
So this massive disconnect between the strict mathematical proof of infinity and the physical reality of a stable universe means physicists must have developed some kind of workaround, right? Like, the math is obviously broken, but the physics somehow works.
Oh, they definitely found a workaround. The fix developed within quantum electrodynamics, or QED, is a highly sophisticated mathematical technique called renormalization.
Renormalization. I hear that word thrown around a lot.
Yeah, it was introduced specifically to handle these exact divergent infinities so that physicists could actually use the theory to calculate real-world interactions.
I really want to make sure we understand the mechanism of renormalization here, because it's often described in pop science as just sweeping infinity under the rug. But the math is a lot more deliberate than that, isn't it?
It is. From a QED standpoint, renormalization essentially posits that the bare mass and the bare charge of an electron at its absolute singularity are indeed infinite.
Okay, so they accept the infinity initially.
Right. But in the quantum vacuum, that infinite bare charge is surrounded by a dense, churning cloud of virtual particles, specifically virtual electron-positron pairs that are constantly popping in and out of existence.
Oh, I see. So it's not just sitting there alone.
Exactly. Those virtual particles act as a screen. The virtual positrons are attracted to the bare negative charge, creating a polarized vacuum around the singularity. And this screening effect mathematically cancels out the infinite bare charge.
Wow.
Yeah, renormalization basically allows theorists to systematically subtract the positive infinity of the self-energy by introducing a negative infinity into the equations.
Wait, they just subtract infinity from infinity.
Basically, yes. The two infinities cancel each other out, leaving behind a finite, measurable remainder. And that remainder conveniently matches the physical mass and charge we actually measure in a laboratory.
Okay, let me try to map this onto a real-world scenario to see if I'm getting it. Is it essentially like looking at a corporation that has acquired an infinite amount of financial debt?
Okay, I like where this is going.
But the accountant realizes the company also has an infinite stream of revenue. So on the balance sheet, the accountant just subtracts the infinite debt from the infinite revenue and happily reports a net quarterly profit of exactly $10.
That is a brilliant analogy.
Yes. It gives you a clean, usable number at the bottom of the ledger, but the underlying accounting is completely illogical. It totally ignores the reality of the infinities.
That captures the operational reality of renormalization perfectly. You are manipulating the ledger to get a usable number. But, and here's the agonizing part for theoretical physicists, that manipulated ledger works beautifully in practice.
It does.
Oh, incredibly well. QED, utilizing this exact renormalization technique, makes predictions that match real-world experimental results with staggering precision.
How precise are we talking?
We're talking about calculating the magnetic dipole moment of the electron and having it agree with physical experiments to 10 decimal places. It is arguably the most successful, rigorously tested physical theory in human history.
Wow. Which creates an incredible cognitive dissonance. If renormalization yields the most accurate experimental predictions in the history of science, it becomes very difficult to argue that it's just a bug. I mean, it's natural to assume that if the math predicts reality to 10 decimal places, the physicists must have actually solved the underlying problem.
And that exact tension severely divided the greatest minds of the 20th century. Which brings us to the perspective of Paul Dirac.
Paul Dirac, a total legend.
Absolutely. He was one of the founding fathers of quantum mechanics and quantum electrodynamics. He won the Nobel Prize for formulating the Dirac equation, which famously predicted the existence of antimatter.
Right.
Yet, for his entire life, Dirac fiercely and passionately criticized the very renormalization framework that made QED so practically successful.
Really? Even though it works so well?
Especially because it works so well without actually making sense. Dirac recognized that getting the correct answer on the final exam doesn't matter if your underlying methodology is fundamentally flawed. He basically argued that subtracting infinity from infinity is an operational success, sure, but a philosophical and physical failure.
So he saw it as a mathematical sleight of hand.
Exactly. Dirac pointed out that renormalization completely fails to explain the physical or geometric origin of the divergence. It doesn't tell us why space-time and electromagnetic fields behave this way at a fundamental level.
You are just shuffling the infinities around on paper until they disappear.
Right, you're hiding them rather than discovering a true physical solution for why the energy of a localized charge should be finite in the first place. Dirac strongly believed that the true answer should emerge organically from a deeper, more refined theoretical framework, not from an artificial mathematical patch.
The frustration Dirac felt really echoes through the history of physics. In fact, the lecture notes from Yingtao Yang refer to this unresolved infinite energy bug as the third cloud hanging over modern physics.
The third cloud, yes.
And that specific phrasing, calling it a cloud, ties directly back to a very famous moment at the dawn of the 20th century involving Lord Kelvin, doesn't it?
It does. Back in 1900, Lord Kelvin gave a landmark lecture where he declared that the beauty and clearness of the dynamical theory of classical physics was obscured by two clouds.
Two specific anomalies.
Exactly. Two highly specific experimental and mathematical anomalies that classical physics completely failed to explain.
Right. The first cloud was the failure to detect the luminiferous ether, the hypothetical medium that light was supposed to travel through.
Yeah, the Michelson-Morley experiment basically proved it didn't exist.
And the second cloud was the ultraviolet catastrophe, which was this mathematical divergence in calculating the energy emitted by a black body, which is ironic because that's another situation where classical math predicted an infinite output of energy that didn't physically exist.
Precisely. And the key takeaway here is that those two seemingly small mathematical clouds could not be patched or swept under the rug with clever accounting.
Right. To fix them took massive paradigm shifts.
Huge ones. Resolving the first cloud required Einstein to completely reconstruct our understanding of space and time with the theory of relativity. Resolving the second cloud required Max Planck, Einstein, and others to invent the entirely new paradigm of quantum mechanics. You don't clear a fundamental cloud with a mathematical trick.
You clear it with a completely new foundation.
Exactly.
And that is why Yang's lecture labels the point charge energy divergence as the third cloud. It essentially proves that despite the operational success of our current models, classical electrodynamics and quantum field theory are fundamentally incomplete.
They have to be.
If the math leads to infinity, the theory is flawed at its roots. The sources argue we need a structural reconstruction of our physics, starting all the way down at the basic principles.
And to be fair, there have been significant historical attempts to achieve that structural reconstruction. Physicists recognize the need for a physical solution, rather than just a mathematical patch.
So people have tried to fix the core equations before.
Oh yeah. The lecture highlights two highly notable early efforts, the Born-Infeld theory and the Heisenberg-Euler theory. Both of these frameworks attempted to resolve the divergence by fundamentally modifying the electromagnetic Lagrangian.
Okay, let's remind ourselves how the Lagrangian operates in this context. The Lagrangian is essentially the master equation of a physical system, right? It describes the state, the dynamics, and how the fields interact and evolve over time.
That's a great summary, yeah.
So if you modify the Lagrangian, you are fundamentally altering the basic rules of how the electromagnetic field propagates.
Precisely. Born in Infeld, and later Heisenberg and Euler, recognized that the classical Lagrangian leads to linear equations. And that linearity is what allows the electric field strength to skyrocket to infinity as the radius approaches zero.
Okay, so how do they fix it?
Well, to fix it, they introduced nonlinear terms into the Lagrangian. Their mathematical goal was to essentially cap the field energy. By making the field nonlinear at extreme intensities, the electric field strength would asymptote.
It would level off.
Yeah, it would hit a maximum allowable value and you get infinitely close to the point charge rather than just diverging to positive infinity.
Okay, let me visualize this nonlinear modification. Is it essentially like looking at the mathematical curve of the electric field accelerating toward infinity and just deciding to hard code a maximum limit into the physics?
Kind of, yeah.
Like, they programmed a cosmic speed limit for electric field strength. The field can get incredibly intense, but the nonlinear math physically prevents it from crossing that maximum threshold.
That is exactly what the nonlinear terms achieve. They impose an upper limit on the field strength, ensuring the total integrated energy remains finite. But, and this is a huge but, there's a fatal flaw in the Born-Infeld and Heisenberg-Euler attempts.
Which the lecture notes heavily emphasize, right?
These theories were purely phenomenological.
Meaning they were constructed backward, they observed the phenomenon they wanted, which was a finite energy, and they basically reverse-engineered the math to produce that exact result.
Without actually knowing the underlying physical mechanism.
Exactly.
It was an empirical guess. Born and Infeld knew the self-energy couldn't be infinite, so they adjusted the Lagrangian specifically to stop the divergence.
But they didn't know why it stopped.
Right. They lacked any logical derivation for why those nonlinear terms should exist in nature. They didn't derive the speed limit from the actual geometric structure of space-time or from any fundamental physical symmetry.
I see. You can't just slap a nonlinear term onto the master equation to avoid an embarrassing infinity.
No, you have to prove why the fundamental nature of the universe demands that nonlinear term.
It's like they recognized the engine was spinning out of control, so they installed a governor to cap the RPMs, but they never actually figured out the thermodynamics of why the engine was overheating in the first place.
That's a perfect way to put it. These theories provided a crucial physical intuition, the idea that nonlinear effects at extreme scales might cap the field, but they failed to reveal the true essence of why the divergence happens.
Which leaves the third cloud stubbornly hanging over theoretical physics today. For a century, we have tried ignoring the infinite energy bug. We've patched it with the mathematical sleight of hand of renormalization to achieve incredible experimental success.
And we've tried hard-coding speed limits using phenomenological guesses.
Right. But none of these approaches have provided a true, fundamental physical resolution based on the geometry of spacetime.
Which brings us to a massive cliffhanger in the source material.
Yes, it does. We have been analyzing the second lecture of Yingtao Yang's Electrodynamic Spacetime Relativity series. But in the upcoming third lecture, Yang promises to unveil a completely new theoretical framework aimed at clearing this third cloud once and for all.
It is a highly, highly ambitious proposal. According to the notes, Yang intends to modify electrodynamics from the ground up by proposing a new, fundamental physical constant.
A completely new constant.
Yes, an absolute limit to electric potential.
Wow. So much like the speed of light acts as an absolute cosmic speed limit derived from the geometry of spacetime, Yang is essentially arguing there is a fundamental limit to electric potential built natively into the universe.
That's the claim. And by deriving this limit from basic principles, rather than just guessing nonlinear terms like Born and Infeld, he claims the framework will thoroughly overcome the infinite divergence problem.
Without relying on any mathematical tricks or phenomenological patching.
Exactly. If a theory can successfully reconstruct our understanding of electrodynamics to natively include a finite potential limit, deriving it directly from space-time structure, it would represent a massive paradigm shift.
It would mean finally replacing the patched-together framework of renormalization with a mathematically clean, geometrically sound understanding of fundamental charges.
It would be revolutionary.
We will certainly be taking a deep dive into that third lecture as soon as it drops to see how the math actually holds up. But for now, we have to wrap up our exploration of this century-old crisis.
The sheer persistence of the point charge bug really forces you to examine how much of modern physics is built on a pragmatic acceptance of flawed foundations.
It really does, and that is exactly what I want to leave you pondering today. Think back to that tiny electron we started with, resting in your palm. Think about the incredible technological leaps we have achieved using quantum electrodynamics lasers, advanced microchips, magnetic resonance imaging.
The math undeniably works in practice.
It does. But if our most successful, most heavily relied upon scientific theories are fundamentally built on top of mathematical accounting tricks designed to hide impossible infinities, what other profound, beautiful truths about the geometry of our universe might we be completely blind to simply because our current equations are good enough to get the right answer?